Good evening, everyone. Welcome back to Starknet Africa's Bootcamp. This is session 5 of Starknet Architecture. It's been an awesome ride so far, and it's been an interesting one. Thank you for showing up, and I believe that we've been learning quite a number of things, right? So in this session, Victor will be taking us through Starknet architecture, where we'll delve into Starknet topology, know a bit more about the whole architecture and how things are happening at the lowest level, and take a look at the independent component that makes Starknet tick and function as a network itself. So I don't know if Paul have anything to add to this. It's going to be an interesting session. And for those of us interested in either cryptography, stacks, or snacks, you get a lot of content in this session and know how sort of works theoretically. So Victor, over to you.
So good evening, everyone. My name is Victor. I'm a blockchain developer, and nice to meet you all. I'm also relatively new to Cairo 1 contracts, but it's been a fun ride so far, and I'm excited to see what we can be able to build. So I hope all of you had a great day, and let's have an interactive class. So if you feel you need to interrupt and ask a question, feel comfortable, or if you feel you need to contribute, feel comfortable. Welcome again. I'll be taking you through today's class, Starknet Architecture. So as Paul mentioned, the previous class you guys covered testing contracts. In this class, you're going to do something a bit different. So less code than last time, and instead you're diving into Starknet architecture. How Starknet works under the hood, what are the different components that work together, and how they interact with each other. We're also going to cover how Starknet interacts with Ethereum mainnet. So I think the biggest takeaway should be for you at the end of this lesson, you should have an idea of how Starknet is able to scale Ethereum and how it stores its data, including a number of other things. So it's important to mention that Starknet is still in alpha. So there are some changes on the way according to the roadmap, which could affect the way Starknet works going into the future. So some of the functionalities that you're going to cover today might change, not too much, but they might change going into the year as Starknet progresses into a full product. So I'll share my screen so that you can start the presentation. I hope everybody is able to see my screen comfortably.
Yes.
Awesome. Yeah, so that's my Twitter. If you want to reach me after the class, or if you want to, yes, you're welcome. And that's how I also look in real life. Just kidding. So this is our agenda for today. We are going to cover the transaction lifecycle, network topology, which is just the different components, the main components that comprise Starknet. We're going to cover proving, which is like the main thing that zero-knowledge rollups are able to achieve. It's also what makes ZK rollups different from optimistic rollups. We're also going to cover data availability and L1 to L2 communication. Okay, so let's start with the transaction lifecycle. So I take it most of us have been able to carry out transactions on Starknet, whether on testnet or even on mainnet. So we are going to focus on mainnet, but I think the process is going to be pretty much the same. So we can see this diagram over here, and this simple diagram covers essentially how Starknet works under the hood. So we can see a few terminologies here that we are going to break down through the lesson. We have the gateways, we have the sequencer, we have the prover, the verifier, and the Starknet core smart contract. All right. So transactions originate from a user wallet and they end up on chain. So that's how this looks in diagram format, what I just said. And so let's start breaking this down. Transaction originate from the gateways, which are the entry points between Starknet and Ethereum. And the transactions are broadcasted to the nearest nodes. The transactions are sent to the nearest nodes. And from the nodes broadcast the transactions to the sequencer. And that's like the first step. You can see transaction received, and then you can see the sequencer. Then the sequencer is able to validate and execute the transactions and create blocks, which are then sent to the prover, and the prover is able to generate zero knowledge proofs of the computation. The proofs are then the proofs are gonna be verified on the verifier, and then they are gonna be sent to Ethereum mainnet. So let's see this on StackScan. So let's go to any transaction. Let's go to some of the recent transactions. So these are transactions which have just been executed 4 minutes ago. So let's break this down. Yes, so at this point, at the second row, you can see there is this row which is called the status. And you have, let me hover over the 5 statuses that a Starknet transaction usually has. So the first one is we have not received, received, pending, accepted on L2, and accepted on L1. So let's break down what that really means. So the first step, when the transaction status is not received, this point means the transaction is not yet known to the sequencer. So when you just sign the transaction in your user wallet, but the transaction has not yet arrived to the sequencer. But Starknet in itself is able to be aware and keep track of the transaction. That's why we have the status not received. Then the nodes are able to forward the transaction to the sequencer, and the status of the transaction changes. So we have received. So at this point, the transaction is stored in a queue together with other transactions, because we know that there are a lot of people who are carrying out transactions on Starknet. So the transaction is stored inside the mempool, similar to what you have on Ethereum mainnet. And from the mempool, the sequencer is able to pick the transactions one by one and carry them out. So the next status we have is pending. And pending it just means that the transaction has been submitted to the sequencer and is in the process of being validated. Validated in the context of Starknet means that the sequencer is able to confirm the nonce and other qualities of the transaction. It doesn't actually go into the actual execution, but it just confirms that the transaction is valid. So there shouldn't be any attacks or any incongruences. For example, there shouldn't be any replay attacks, or your wallet status or your wallet balance should be updated and your nonce should be up to date. So accepted on layer 2, this is the point that you arrive once a transaction has actually been validated and has been added to a block, the block which is going to be submitted later to the proof, as we saw in the earlier diagram. And then the final stage of a transaction is accepted on L1. Accepted on L1 means that the transaction information, in this case, you're talking about the proof that the computation was accurate, has finally been submitted to Ethereum. And we can see for this transaction that this has not yet been activated. But if you can go and check some older transactions, you can see that they have been accepted on layer 1. So let's just confirm that. Yeah, so here we have some older transactions. This one is dated November 2021. And we can see that finally this transaction is accepted on layer 1, accepted on L1. So this transaction is stored on Ethereum mainnet. Are we together up to this point? Yeah, so if you have any question, you could just interrupt me and ask me. So there are also other statuses of transactions on Starknet. So sometimes not all transactions are able to go through. I'm trying to use this opportunity to identify such a transaction so that we can be able to see the status of such a transaction. Just a second. Okay, you can see we are lucky. We can see that the first status of these dates that I've selected is reverted. So let's look at that transaction again. So we can see that the transaction is reverted. So there are three statuses that arise when a transaction is undergoing execution by the sequencer. We have rejected, we have reverted, and succeeded. So let's start with rejected. So a transaction is rejected when it's received by the mempool. The mempool is where the sequencer receives the transaction from. But the sequencer is unable to validate the transaction. So for example, there might be inconsistencies with the nonce of the transaction, for example. So the status for such a transaction would be rejected. The other execution status is reverted, what we have here. The transaction passed validation, but failed during execution. So it can fail for whatever reason. Maybe there might be some inconsistency. Maybe you are calling functions which, for example, the interfaces don't match. So it could be anything. So a transaction which is able to be validated but the execution fails is gonna be reverted. And finally, the last execution status is succeeded. A transaction which succeeds is a transaction which is successfully executed by the sequencer, and it's included in a block which is submitted to the prover. I hope we're together up to that point. So acceptance on L1, which is like the final step. So let's go back to some of the transactions that you're checking. So up to this point, the transaction exists on Starknet. When a transaction is finally sent to L1, it means that the transaction cannot be changed totally. Like once a transaction is forwarded to layer 1, it's forwarded there permanently and nothing can be changed. So that's like the final step, and that's when a transaction is considered final, when it's carried out on Starknet. When you're executing a transaction on Ethereum mainnet, you'll notice that I think the finality time is around 12 minutes, but on Starknet, the finality arrives when the transaction is finally accepted on layer 1. Okay, so we've covered the transaction lifecycle. If anybody has any question, it's pretty much simple. If you've ever carried out a transaction on Starknet, I'm sure you could have come across this interface before. So that's just what we've covered. So let's go back to our slide. Okay, so for the network topology, we are going to cover the two core components of Starknet, where we have the sequencer and the prover. If I may scroll up for you to be able to relate using our initial diagram, we have the sequencer, which executes transactions and creates blocks, and we have the prover. We're going to see what the prover does in a few. So yeah, this is another diagram. Okay, so before we dive into the sequencer, let me just mention that we have nodes on Starknet. However, nodes on Starknet are different from nodes on Ethereum mainnet. On Ethereum, nodes are what actually carry out the execution of transactions. But on Starknet, they are mostly used to track the state of the network. So they're able to do so by replaying transactions, relying on the consensus of layer 2 validators, and they can also be able to reconstruct the state by using the proofs which are stored on layer 1. So these are three different methods, and the methods come with their own share of the fair share of pros and cons, so it depends. So it depends on the needs of the user. So let's look at the sequencer. So the sequencer and the prover are the two main components of Starknet. And at this point, you're able to see the distinction between Ethereum mainnet and Starknet layer 2. Because on Ethereum, once your transaction is executed by the nodes and included in a block, that is final. There's nothing else that you just need the passage of time and the addition of further blocks for your transaction to be final. But on layer 2, something is different because layer 2s, they have a different role. Their use is mainly to scale Ethereum. So to be able to do so, they use these two components, the sequencer and the prover. So the sequencer is responsible for executing transactions and processing blocks. So these are similar to the validators in Ethereum. And because Starknet is able to scale Ethereum, one way that Starknet is able to achieve this is through the sequencer being able to process transactions way faster and more transactions than a node is able to do on Ethereum mainnet. So this is one of the ways in which Starknet is able to scale Ethereum, is through being able to handle a lot of transactions concurrently. So the prover, on the other hand, is to be able to provide a guarantee, a mathematical guarantee of the validity of the transactions on the blockchain, which are finally settled on Ethereum. One thing we have to note is, and we'll dive in and we'll be able to understand once we dive deeper into the sequencer, is actually, let's just go straight to the sequencer. So the sequencer is an off-chain server, and it's outsourced because it demands a lot of resources. So the sequencer is able to order, validate transactions, and bundle them into blocks. The sequencer is very critical because that's how you're able to process transactions very fast. So to validate transactions, the sequencer runs the Cairo operating system, which is sort of like the EVM, but it's different because Cairo uses different machine code. So the blocks which are produced by the sequencer are submitted to layer 1 as compact proofs, and that's where the name rollups come from. So another important thing to mention is that transactions are run sequentially and not parallel. And that's how you achieve scalability. So currently, the sequencer that's used by Starknet is not open source, and it's run by Starkware. So there are plans to open source this, and that will definitely help with decentralization. So there are other sequencers which have been created by the community in open source, and these include Madara and Kraken. So these are not yet in production, but they are critical for the upcoming development of Starknet. I think I'm more familiar with Madara, which is mainly tailored towards development of layer 3s, which are, I think layer 3s are appchains which are going to be built on top of Starknet. I'm not very sure about Kraken, but I know it's also going to be critical to the ecosystem going forward. So do you have any question up to this point? Okay, let's go. So let's look into the prover. As I mentioned before, the prover provides the mathematical guarantee about the validity of the block transactions which are finally settled on Ethereum. Why is it important for us to prove transactions which are carried out on Starknet? You can see that the sequencer which processes transactions on Starknet is off-chain. That means people cannot be able to track it, or people cannot be able to see how it actually works. So you need to be able to confirm to other people that the computation is accurate. And that's where the prover comes in. The prover is also the point at which we are able to distinguish between optimistic rollups and ZK rollups. Optimistic rollups, we have most famously, we have Optimism and we have Arbitrum. Both of them also have the sequencer, but they don't have the prover yet. Instead, they have a different mechanism for proving that their transactions which are carried out on their blockchain are valid. So for optimistic rollups, I think they use what are called false proofs. I'm not very sure about how they work, but I think the state updates are posted to layer 1. And if nobody challenges them within a number of days, let's say 7, that is taken to be final. So that weekly delay, that's how optimistic rollups are able to achieve finality. But that's not the most ideal, because now, until a week passes on optimistic rollups, you cannot be very sure that your transaction is valid. And actually, most optimistic rollups are maintained by multi-sig, which can be able to also censor transactions. So it's due to this point that we have proof systems similar to what Starknet has being developed for optimistic rollups, because these are the end game of proving that your computation is legitimate when you are scaling Ethereum on layer 2. So what does the prover actually do? So the prover is in charge of receiving the blocks, which it receives from the sequencer. It processes them again, but it does this somewhat differently. And it generates a proof, and the proof is sent to Ethereum. Now, this is very simple, because what actually happens at this point is very mathematical and is very, you're going to dive into a lot of math and a lot of cryptography. So, just a second. So Starknet uses a proof system which is called the zero knowledge stack, which I'm sure most of you have heard about, to verify the correctness of transactions. And it's able to do this without disclosing any confidential information, and thereby improving the privacy and security. So stacks are a privacy-enhancing technology that reduces the amount of information that needs to be provided between the user and a scaling technology, allowing proofs to be verified faster because they don't contain the full amount of information for non-private systems. So we also have something similar to stacks, which are known as snacks, but these ones, I think stacks, which are what we use on Starknet, are more bulletproof than snacks. You can find snacks being used in earlier blockchains, including, I think, Zcash is the most famous blockchain which uses snacks. So yes. So what happens in the prover is like highly mathematical. So you have the prover usually takes the execution trace of the transaction, it blows it up and does some math on it, and is able to verify the execution without using all the input details, and is able to create an output file which can be used to verify that the execution was actually legitimate. So today we have two main provers which have been live on mainnet for a while. We have the Stone prover, like that's the main prover on Starknet, and it has been live since 2020. It's what has been used by applications such as DYDX, ImmutableX, and I think Sorare is the other application which has been live since that time. And this was recently declared open source, I think a month or two ago. It's written in C++. And we also have another prover which is also used. It's called the shared prover. So the shared prover is built on top of the Stone prover, and it allows applications written in Cairo to be able to be proved together, sort of like ride sharing. So it batches transactions together, and it's a concept known as recursive proofs. So this also adds to the scalability that Starknet is able to achieve for transactions. So the shared prover also carries a lot of load for transactions which are on Starknet. Are we together up to that point, I hope? Okay. So there's another component which we should be able to which we should be able to cover, and it's called the verifier. And this is critical to how the prover works. We noted that the prover is able to generate a file which is able to confirm that the execution done by the sequencer is accurate. So the prover works closely with the verifier, and the verifier is responsible for verifying, as the name suggests, the correctness of the transactions which are going to be sent into Ethereum mainnet. So the verifier is essentially part of the stack system, the stack proof system. And we have two main verifiers on Starknet. I think we have one which is written in Cairo, and we also have a verifier on mainnet. Yeah, so the verifier is also critical to the scalability that Starknet is able to achieve. So it's also a critical component. Okay. Okay. Yeah, so as we summarize, so proving on Starknet, we can see that a smart contract execution is included in a Starknet job, which basically is like a cron job, which is further included into the SHARP. SHARP is the acronym for the shared proof. So SHARP, like pretty much like the other components on Starknet, is proven on chain and verified is proven off chain and verified on chain. Okay. Okay, so let's go to the next section, which is data availability. So the state that is maintained on Starknet, it has to be stored somewhere. And I think it's a general consensus that Ethereum and Bitcoin have the strongest security in the space. So you can't compare it with other blockchains like Solana or maybe Polygon. So the state on Starknet is stored on Ethereum. As I mentioned earlier, there are updates which are supposed to come later on in the future, and there could be an option where you can store the state of your Cairo program on Starknet itself instead of storing on mainnet. The only difference is it's gonna be cheaper for you to store your application on Starknet instead of storing it on Ethereum mainnet. But at least Starknet is going to try to enforce some security guarantees similar to what you automatically get when you store your program on Ethereum. So because state is quite huge, it's not really advisable to actually store like all the transactions in itself. It's actually instead what Starknet uses is being able to store the hashes of all the computation that are carried out on Starknet. I think right now, if you try to run an Ethereum node, I don't know how big it is, but it should take you a while for you to be able to synchronize the Ethereum blockchain state. It should take you a while. It should take you a few hours. And this also brings us to one of the challenges that arise with blockchains, because all the data is stored in the blockchain. The size of the blockchain will keep on getting bigger and bigger. So this is an area of research, and going forward, there are projects which are trying to find a way to be able to trim the data that is going to be stored on the blockchain. So it's an area which is still under development, but it's very critical. And what Starknet are able to do by using hashes instead of actually storing the data is like one of the compromises that one of the approaches that projects are trying to make to be able to solve this challenge. So one of the challenges that come with being able to avail the blockchain state is you need to be able to have like at least a minimum number of people who are able to validate the network or keep the entity afloat. So how are you able to achieve this? And to be able to do this, this is the point that Starknet is able to leverage Ethereum, and the state is published on Ethereum. So what are actually published, the hashes that we just mentioned are usually known as state differentials or state diffs. And these are what can be used by nodes. For example, if I want to become a validator on Starknet today, I can be able to rebuild the state of the network by running a node and deriving the information from the proofs which are stored on layer 1. However, publishing on Ethereum mainnet is still very expensive. It's very expensive, and as you can see, 98% of transaction costs on Starknet go towards paying for the gas fees. So this is also an area which is a potential area of research. And I think it's mentioned in the roadmap that the Stark token could instead also be used to pay for gas fees. Perhaps that could help out with this. So we have like two main types of rollups. Okay, the validity rollups. This is like what Starknet is able to achieve. And we also have others which are called Validium. So here you are able to avail the data off chain, but stored within like a blockchain or a program that's like achieves some minimum security and decentralization guarantees and safety guarantees. And like the most famous such project is Celestia, which has recently launched. So we also have other approaches towards scalability and evolutions, whereby two state roots are published, and state roots we refer to the macro roots, similar to what like is used on layer 1. So here we track the state that has to be published to layer 1 and one which is gonna be sent off chain. So we're not going to dive too deep into this. I'm not too familiar with this, but it's good for you to just be aware that it exists. So we have an upcoming Ethereum improvement proposal rather, which is called EIP 4844. And this is meant to make data publication on Ethereum cheaper. I think this was supposed to arrive some time this year, but I think it's been postponed to Q1 next year. So this would really help layer 2s and make them even more cheaper. And just as I mentioned, the data when published to Ethereum can only be kept briefly, like this is one approach, and then it's also deleted. And this brings us to like, I think this is a side of research which is just within the broader Ethereum community, whereby we are going to have a data market going into the future, because being able to store and avail this data is going to be critical. If, for example, a lot of transactions such as financial transactions are going to be carried out on Starknet on Ethereum, the amount of data to be stored is going to be even larger. So being able to avail this data is going to be critical, and in a manner that ensures that the security and immutability is maintained. So this upcoming Ethereum improvement proposal is like one of the most important developments on the horizon. So hopefully we're going to have it in the next, maybe by Q1 next year, Q1, Q2 next year. Let's see. Yes, so data availability in summary, it affects the network resilience and the decentralization. So we've looked at the different approaches. We have the validity rollup, which relies on layer 1 to publish the data. A good example is Starknet. Validiums rely on off-chain mechanisms. And we also have a hybrid between the two, which is called volition. We also covered the Ethereum improvement proposal, 4844, which will lower the cost for on-chain data. Okay. So finally, how are we able to communicate? How do we have communication between layer 1 and layer 2? So why is it important for us to be able to communicate between different networks? So one of the main criticisms for layer 2s has been the fragmentation of liquidity. So you need to move assets from one chain to another, and you can't easily interact with assets on another chain. And interacting with assets on another chain introduces a lot of risk, cross-chain risk, because different chains have different security levels. And also moving assets between different chains is very risky. Like we know, bridges are very susceptible to hacks, and over the past year, some prominent bridges have been hacked and a lot of money has been stolen because the process of moving tokens from one chain to another involves locking tokens on one chain and minting an equivalent number of tokens on the other chain. So the smart contract that holds the token on one chain is vulnerable to attacks, and a number of hacks over the past year or two have been targeted at bridges. And it's a general consensus in the community that bridges are not sustainable into the future. So we need to look for a different approach. And that's why we have projects which are exploring cross-chain messaging. I think the biggest one is Layer 0. And we also have Chainlink looking into that. I think Circle for USDC is also looking into that. And they have a way of availing Circle across different chains in such a format such that you reduce the bridging risk. Okay, so let's go over how Starknet is able to communicate to Ethereum. So to be able to communicate in Ethereum, Starknet is able to send a message to the Starknet core smart contract, which is stored on Ethereum layer 1. And this is part of like I don't know what's the word. I don't know the word for the native system calls, but being able to send a message to layer 1, like it's ingrained as part of Starknet, and you can see it. Send message to layer 1 where you have the true address, and the payload. Yeah, so similar to what we observed on transactions previously, you can be able to track your message to layer 1 on the block explorer, such as StackScan or Voyager. Yeah, and it also passes through the different stages. So you have sent, where it's registered by Starknet, but it's not yet visible on Ethereum. And then pending, which is registered on Ethereum and can be consumed on layer 1, and consumed when it's finally received on layer 1. Yeah, so when Starknet state is updated on Ethereum, all the sent messages are passed as pending. And you can be able to track this via an event on the Starknet smart contract. Some of this information can be used by the nodes later when they want to be able to track or to be able to rebuild the state of Starknet layer 2. Yeah, so similarly to what you just mentioned, this builds up on that, and we have a nonce which is able to keep track of all the increments using a counter. Yeah, and this is the function on layer one. So this is solidity. This is the function that is able to consume the information which is sent from Starknet. Yeah, so messages are transmitted with proofs, the zero knowledge proofs that we mentioned earlier. Yeah, so proofs are supposed to be sent more frequently on mainnet. I'm not really sure how frequently they are sent on mainnet, but yeah, you can see on testnet takes about every 2 hours. So the idea is to reduce this frequency so that finality is achieved faster. In any case, this is way faster than what you're able to achieve on optimistic rollups. And that's why the end game for layer 2s is having zero knowledge proofs for most layer 2s implemented. Okay, so what happens when you want to send a message from Ethereum to Starknet? So similarly to what we encountered before, you have to specify the recipient, which is just the address, and you also have to specify the specific function that you want to call. Yeah, it takes a while, like 10 block confirmations for your block to be sent to Starknet. And the recipient, which is the address which you are calling, which is part of the argument parameters of the function, needs to be able to implement a specific receiver function. So it's like a callback function, which should be available in the recipient address. And here we can be able to see the relevant Cairo 1 code. So we have the L1 handler, which is an inbuilt macro on Cairo, and it can be used when you are creating functions that are specifically tailored to receive messages from layer 1. So it's like a decorator, the same way you have external, or yeah, same way you have external. Okay. Yeah, so layer 1 to layer 2, like Ethereum to Starknet messages are directly consumed, and they are quite difficult to debug. Maybe this might change with future iterations of Starknet. And this brings me to the end of the presentation. I've speed passed through it, but I hope you guys are able to learn. If anybody has any question or somewhere you want us to revisit, it would be great. Okay, does anybody have any questions? Okay, Kevin, are you there? Okay, let me invite Kevin or Paul to take over now. if there's no
Yeah,
other question.
I'm actually here. Okay.
Okay.
Yeah, great presentation, man. I mean, you made okay. So there's a question in the chat box. Probably check it out.
Okay. Okay, so Francis is asking, can you repeat how transactions are approved? Okay, so let me think I've written something on this. Just a second. Yeah, so basically proving is quite mathematical, but maybe I'll go deeper into the stone prover. So there's actually an issue which I'm doing for the Starknet book, and I'm gonna refer to it right now. So there are four main building blocks of the stone prover. We have the stack, which is the stack proof. I think is the acronym for the succinct. I don't know the full acronym. And then we have something which is known as an AIR, algebraic intermediate representation. So we also have the Cairo AIR and we have the built-ins. So let's go into that. So the stack is a protocol, I think something like HTTP, that enables you to prove computation between two parties and come up with into a certain output. And stacks basically are what hold Starknet together. Next, we have the AIR, like algebraic intermediate representation. So for the guys who are into mathematics and cryptography, so this is your opportunity. So the AIR describes so when you actually execute a transaction on Starknet, similar to what you have on mainnet, you can have the program counter, which basically breaks down each and every step of execution. So you have each and every opcode and what it's able to do. On Ethereum mainnet, that's where it ends. Like you can have your push zero opcode, you can have your dupe opcode, but on Starknet, it doesn't end there. Like where you generate the opcodes, that's where the sequencer is. But when you get to the prover actually does some mathematics on the actual steps of the execution. And to be able to achieve this, the prover is able to represent all the steps that you took during execution, all the different opcodes, and the prover represents all the execution using polynomial functions. Using polynomial functions. And then these polynomial functions are what can be further be used they are supposed to meet certain standards such that like they are functioning correctly. For example, if you have a formula, for example, if you have a graph, y is equal mx plus c, for example. So you're able to represent the execution in certain functions, and those functions are supposed to fulfill certain mathematical qualities, certain cryptographic qualities. So this representation of the polynomial constraints, they change depending on the computation, and they can become technical. The more the computation of the more whatever you are implementing becomes complex. I don't know if I'm making more sense, or I checked out, there's a presentation by on Starkware YouTube where the stone prover is actually discussed. It came out when the prover was made open source, so that's why I checked it. I'm still trying to understand it a bit. So once you represent the execution using polynomial constraints, so at this point, Okay, so polynomial constraint, that's one way to go about it, but it's also a bit technical. And Starknet uses CASM and Cairo Air. So Cairo Air is similar to the algebraic intermediate representation that we just covered earlier, but it's a bit simpler to execute. So simpler in terms of you have some built-in functions. And I think if you've written some code or read through the docs, you've seen the word built-ins, like range check built-ins or something of the sort. And this is where they come in place. So to be able to execute, to be able to generate a proof, you need the Cairo assembly, which is like the EVM, an instruction set. But this is specifically designed to be efficient for generating proofs. So you need that, and you also need representing the execution of the transaction in Cairo Air. And that's what you're gonna use to be able to. So let's just go over how to use the prover. So firstly, you just compile the code using Cairo compile. Then you run the compile program to generate the prover input files. So there are certain input files that you need to be able to run the prover. The input files, you have two configuration files, one controlling the proof itself, the parameters, and the other controlling the prover, which is going to generate the proof. And when you, okay, so using the input file from before, you run the prover to generate start proofs, and these are in JSON format. Then using the proof, you can be able to run the verifier. So the proof is actually a JSON file, and it has a certain field, I think, the proof X, which is used for verification. Yeah, so a lot of this stuff flies over my head, but there's a presentation on Stack by YouTube that I could share in the group for you to see and learn more about it. I don't know if I've answered your question, but I've given it my best try. I know there are people who are more into the cryptography part of it, and who could maybe elaborate better. Yeah, most of this other stuff are even more low level. So yeah, I hope I've answered your question, Francis. Any other questions? Okay, let me just look for it right now. I'll get you on the call. Um, yeah, so there's this open issue on provers on Starknet, on the Starknet book on GitHub. Yeah. So let me just share the link. This is the link I just shared on the chat. So you can have a look. Okay. And let me also share the link to the prover issue. There are other links there as well, which you can check out. Are there any other questions?
Okay, seems there's no further question. Good presentation, man. And yeah, we are coming to the end of our bootcamp. The last class will be next week, same time, same dates, and it's really all about front end. Yeah, front end. So we would have Wise Musa take on the class next week. So we hope to see you guys there. And also we are working on having an extra section, but this would be, we'll have the Saturo team give us a quick intro on their project, and as well show us like how we can contribute on their project. So we're going to make announcements and also send out emails about this. And as well, after that, we'll also have plans to make sure that anyone that graduated from this, our bootcamp, get to have interactive section with the Starknet Foundation team. We have all the plans for like when this bootcamp ends, like next week. So we look forward to seeing you all in the next class, and do have a lovely night. Yeah.
Goodbye.
Yeah. Good night, Victor. Yeah, bye.